We're now going to take a look at composite functions. Before we take a look at the operation of composition, though, I just want to look at a couple really simple operations that you're acquainted with: addition, subtraction, multiplication, division, just because the notation is a little bit important here. But imagine you have two functions. I haven't defined the domain or anything on here. The notation that you see here is somewhat unsurprisingly saying if you add the functions together, you have a new function defined by x. So f plus g of x is f of x plus g of x. So you could say 2 minus x plus, again, not bad to write it in parentheses. It's a kind of a wonky x, sorry. And these can't really be combined in any meaningful way, so you can leave it like this. Of course, there are different ways to write it. You need to make sure that you're being careful as you move into the other operations that are not quite as nice with some of the laws. Like this is f times, or f of x times g of x. And if you don't use parentheses here, I'm going to purposefully not write parentheses times 1 over x. This is obviously implying a different thing than the full function times the full function. So be careful to FOIL or distribute as needed and appropriate. So 2 over x minus an x over x is 1. Okay, and this last one is the function f of x divided by g of x. I haven't included, I haven't included subtraction. I mean, you guys know how to subtract, but it's the same kind of thing. 1 over x. Be, again, careful with this because remember, dividing by a fraction is actually multiplying by the reciprocal. And the reciprocal of 1 over x is just x over 1 or x. And then distribute. Okay, subtraction, be careful with parentheses, etc. But in general, this is just rather simple operations on functions. Pay attention to the order of operations that you are acquainted with. But what we really want to look at here is composition. This will be incredibly important going forward, recognizing the structure of different functions that are perhaps a bit more complex, maybe adding them together. So here are the same two functions, and you'll notice that you have this little circle. And this is read following. So you put one into another, and just like with the laws of parentheses or the order of operations in general, you work inside out as you simplify. So you could write it either way, a little bit clearer, I think in the circle way, it's a little bit more formal, but it's actually just saying if you put parentheses around the same way, which function is going into which. So this could also be written as f circle g in parentheses of x. And it's saying that you take the function g and you put it in for x. So here's g of x, and it's going into f of x. So the outside function is the f, and then of course, just like as if you had a number or whatever else, you would put in for x every time you see it, g. Err on the side of more parentheses than too few. This can't really be simplified all that much, but we'll write it out here, distributing, well, nothing really distribute. 2 minus 1 over x. You can go the other way. You can compose with itself. So this would be as if you had g inside of f inside of g. Ooh, I'm speaking. So this goes into this bigger function. G is on the outside. So the outer function is g, 1 over, and then every time you see x, we're losing my red pen here, we're going to put in f. Okay, nothing I can simplify here. I could write it in black, but why? And this is the same thing. If you did want to write it out with two different colors, sure, whatever, but we're just putting g back into itself. So every time you see x in g, you put in g again. And 1 divided by 1 over x is x. So that's what composition is. You're putting one function into another. There are other ways to think about this. Assuming I can turn the page here. I've got too many pens in my hand. Okay, well, we'll get to some other representations in a second. You can also do this with a value in for x. It's just kind of putting in more. You have the option of first putting 3 into g. How about I write this out? So you could do f following g of 3. That's the same thing. as f following g of 3. Sometimes it helps to write things a little bit smaller so you see what goes in where. And so you could do g of 3 first, which is what I will do in this particular case. You could find the full function, f following g of x, and then put 3 in. Those are the same thing. So if I first put 3 into g, I would get 7, and then I would put 7 into f. Okay, I won't write it down because I would like to be a little bit more pedantic with the way I write it down, but that's what we're doing. First, put 3 into g, and then put your answer into f. So, but f is on the outside, so I'll write f, and g is on the inside, and every time I write x and g, I wrote a 3. Okay, and we could put it like that. So 3 is into g, and g is in f, and we do get the same thing. Okay. But again, you could take it in different steps here. You could look at it as tables or graphs as well. It's really just the idea of understanding inputs and outputs and what comes first in the order of this operation. One is being put into the next one. So g following f of 4, I'll write it out this way just to show you the kind of thinking here. Well, f of 4 means if I put 4 into the function f, so here's x is 4, and if I put 4 into the function f, I get out 2. This is the output in the table, kind of like saying, well, here's x and here's y. But because you've defined these as different letters, it's a little bit easier to write which function goes where. So the output of f of 4 is 2. And then I could say, okay, well, if I put 2 into g, here's x is now 2, here's g, I get out 1. So you could look at it that way as this input-output machine. Same thing with these different functions. We have f of x, g of x, and h of x. This particular problem is asking us to look at g and h. So the first thing is I want to find out when x is 7, what is h of x? So what is y when x is 7 on the function h of x? 5, 6, 7. Well, that's 0. If I put 7 in for x on h of x, I get out 0. And then I could say, okay, if I put 0 in for x and look at where it hits g, here's 0, and here's g, I get out -1. So input, output, different ways of looking at it. Not all that challenging. If the notation is a little weird, take a look at it in a different way. And unsurprisingly, because this whole conversation is about inputs and outputs, of course that affects the domain and range. It's probably easiest to just take a look at the function as if it was originally given to you that way, if you have that kind of structure. But the big idea is, of course, if you're inputting something into the inner function, you're limiting what you can get out and put into the next function, depending on what the function is. And the way this works out is that the domain of any composed function is just going to be either the same or a subset of the inside function. You can't possibly have more possible x's than went into your original function. You are already limiting it. And in a similar vein, the range of your composed function is going to be either the same or a subset of the second function. You can't get out more things than you would get out on a more basic function here. You can take a look at these here. You'll see in our originally defined functions that they're a little bit less restrictive than if you have compositions of functions. You can take a look at that. I'm not going to walk through it. Of course, if you're getting these functions originally, you didn't need to know that these are composed functions to figure out the domain and range. Just thinking through these, knowing that you can't, for example, have negatives in an even root, or you can't have a range with an absolute value that's negative because it makes everything positive or 0. And you're just adding more limitations to inputs and outputs in these particular case. Okay, so that's what composition is. Not that challenging in my opinion, but of course, we'll see how it goes.